This conference will now be recorded.
Hello everyone. So the topics we are going to discuss today: ionization, enthalpy, as you can see the topic here. Then electronegativity, melting point, boiling point of group 13 elements, density of group 13 elements, and then all together in a single table we will see all the important physical properties and atomic properties. After that there will be oxidation state of group 13 elements and trends in their chemical reactivity. Okay, so let's start with ionization enthalpy. So in the last class we just have some primary idea about ionization enthalpy, but we will finish this today. So when we are saying ionization enthalpy, it is obviously the first ionization enthalpy of group 13 elements. Now just remember once more, the general electronic configuration is NH2NP1, and before that we have noble gas configuration. Depending on the value of N, the noble gas may be different. Now the first ionization energy means you are basically removing the electron, single electron present in NP. When you are removing it, you are reaching the configuration Ng within third bracket and then NH2. But if you compare it with group 2 elements, that is alkaline earth metal elements, where the general electronic configuration is after noble gas, it is NH2. Okay, so here it is mentioned the first ionization energy of the elements of group 13 lower than the corresponding elements of group 2. Now if you are thinking that group 2, and now when we are talking about group 13, it is basically in the right hand side, and in the periodic table we know when we move along the period from left hand side to right hand side, ionization enthalpy in general increases because of the decrease in size. So removal of the electron, the most loosely held electron in the valence shell, that is very difficult. But here you are seeing the opposite thing. So what is the reason behind this exception? The reason is when you are removing electron from this configuration, that is group 13, you are reaching this configuration, which is fully filled because it is NH2. But if you are doing so for alkaline earth metals, that is group 2, basically you are breaking the fully filled configuration of NH2, which is energy requiring process. So that is why the first ionization energy, that is the first electron removal, if you compare group 2 and group 13, obviously for group 13 it is easier. So that is why IE value is lower. Okay. So in case of group 13, for the first ionization energy, the electron has to be removed from p orbitals. But in case of group 2, the s electron of the same principal shell has to be removed, which is more energy requiring process. So this is the explanation. On moving down the group, now what happens? When we are moving down the group, that means we are moving from boron to aluminium to gallium like this. Our normal expectation is size increases. So that is why now the electron that you are trying to remove, it is far from the nucleus. So it must be easier process, and that is the general trend we know. In case of group 1 and 2, that is the last chapter that we have finished, S block I am talking about. There also we have seen it is very simple. Down the group, ionization energy, it smoothly decreases because of increase in size. But when we are discussing group 13 in P block, moving down the group, you will have two discrepancies from the general trend. So what we expect when you are moving from boron to aluminium to gallium, then indium, thallium, the discrepancy is observed between these two, that is aluminium and gallium. The first discrepancy, and the second discrepancy is between indium and thallium. Now look at this. Here when from boron to aluminium there is a large jump, right? And it is actually related to the size. Remember, from aluminium to gallium when we move, it is not that size is high, size is actually low. When we have discussed in the last class atomic size, remember there we have mentioned the actual values from which it is clear is lower, that is the size is less. So obviously ionization energy, the normal trend we cannot expect when you are moving from aluminium to gallium, though it is not that very highly different there from each other, but there is a slight increase, as you can see. So it is around here but if you draw a dotted line, it will be slightly greater. Then again we have some discrepancy in between these two. So from indium, when you are moving to the next element, basically what should happen? There should be decrease, but here you can see clearly this value is high. So these two are the discrepancies that we observed in this trend. So to understand the reason in detail, obviously the size of gallium, it is slightly lesser than aluminium. This is the reason. Another way also you can explain it. In case of gallium, just before gallium there is fully filled 3D subshell, and before indium and TL, you can see 4D is there, 4F, 5D is there. That means because of poor screening property of this D and F, the attraction of the nucleus for the outermost electron, that will be very high. So that is the reason for these two discrepancies. So just have a look here. This is due to inability of the D electrons and F electrons. So when I am saying D, it is basically 3D electron for gallium and 5D electron for TL. As you can see from this picture, just look at this picture, you will understand. And what about F electrons? F electron, it is only applicable for TL. So these D and F orbitals, they have low screening effect, and that is why they will not be able to compensate the increase in nuclear charge. So it is true that when you are moving down the group, because of increase in atomic number, nuclear charge, there is a positive charge, proton number I am talking about, that is very high. But another factor is there, when you are moving down the group, size increases. But this size increase factor and the increase in nuclear charge factor, if we compare these two, in most groups, in S block also you have seen, the atomic size in increase factor, it can compensate this nuclear charge. So that is why down the group, normal trend we have seen ionization energy decreases. But here, because of this low screening effect, it will not be able to compensate this increase in nuclear charge. Okay, so these are the reasons. So remember, it is not smooth decrease. There are two discrepancies. Next property, electronegativity first, then we'll see melting point, boiling point. Elements of boron family, that is group 13, they are more electronegative than the elements of alkali metals and alkaline earth metals. And it is expected because alkali and alkaline earth metals, they are from S block, which is at the left hand side of the periodic table, and boron family is basically 13, which is in P block, that is in the right hand side. So obviously non-metallic character will be introduced. Compared to left hand side, in right hand side, more non-metallic character is there. So they will be more electronegative compared to group 1 and group 2. When we move down the group, how the electronegativity changes? When we move down the group, first, there is a decrease from boron to aluminium, and that is again expected. Because from boron to aluminium, when you are moving, basically more metallic character increases down the group. So that is why electronegativity should decrease. But see, again discrepancies we have. Then increase marginally. Now again, the explanation behind this unusual electronegativity trend is the atomic size of the element. Remember, aluminium and gallium, there is some discrepancy in the atomic size we have seen. So that is why the normal electronegativity trend, that is not observed. So normal trend is like this. When you are moving from boron to TL, it should decrease like this, but that is not happening. Only this part you can see, it is as our expectation. But then again, it is increased, though the increase is not very high, because it is not that it is increasing because metallic character is suddenly decreasing. No, that is not the case. Obviously down the group metallic character increases, but because of this atomic size factor, and also remember the poor screening capacity of D and F orbital, because of these factors, the normal trend of electronegativity decrease down the group, that is not happening. So there is slight increase. It is not very high increase down the group. There is marginal increase. What about melting point? There is no regular trend for melting point of these elements. But if you consider BP, that is boiling point, then it is decreasing down the group. Okay, so no smooth trend for MP, but smooth decrease down the group for BP we can observe. Now have a look in this table. These are the elements, then melting point and boiling point. So when it is boiling point, there is smooth decrease 39232740. Okay, but what about melting point? This is exceptionally high. If you look at the other values, they are lesser than 1000, around 300, 400, 500 like this. But it is, just look at these two values, drastically different. So there is drastic difference between these two. But after that, then there is decrease, then again increase, again increase. So there is no such regular trend. Now, why there is so much, you can see so much high value for boron, 2453. Why it is so? Because of very strong crystalline lattice, boron has unusually high MP. But other members, if you consider, they are soft metals. Their melting point is not very high, and they are having high electrical conductivity. So among all these, you cannot say boron is metal. It is not under metal category because it is the first element. So, and also it is in the P block. Down the group metallic character increases, that is fine, but boron is not metal, and there is strong crystalline lattice present. That is the reason for its high, not just high, unusually high melting point. And there is very interesting thing about gallium. If you that is, if it is room temperature and if it is summer season, you can see gallium, it is in liquid state, because 303 in Kelvin, that means if you convert to degree centigrade, you can understand it is very close to room temperature, right? So that is why, and it is also lowest among all the melting points that you can see in this column. It is lowest. So as it is lowest and it is close to room temperature 25 degrees centigrade, so when it is summer season, then room temperature is slightly high, then we can see it is existing as liquid. So it is metal, but it is still liquid. So this is unique feature. Density, this is the last property we are going to discuss. Due to smaller atomic radii, the elements of group 13 have higher densities as compared to group 2. So compared to group 2, group 13 size is small and density is high. Now when we are talking about density, it is basically mass divided by volume. So here mass is increasing, that is fine, but see, volume is very that is, radii is very small, and radii small is means volume is also small. So when volume is small, that means this denominator, it will be very small, and as a result density, that is the ratio, will be high. When we are moving down the group, the densities increases because of increase in atomic mass of the element, and it outweighs the effect of increased atomic size. Now when you are moving down the group, basically M is increasing, V is also increasing because down the group size increases, we know. So when both are increasing, don't think that density it will remain almost same. It is not that. The rate of increase for mass and the rate of increase for volume, if you compare, then it is observed that the rate of increase in atomic mass, it is outweighing, that is overcoming the effect of increase in atomic size. So the rate of volume increase is not so high, but rate of mass increase is high. As a result, the densities down the group increases. So until now we have discussed different properties: ionization energy, atomic size, electronegativity, melting point, boiling point. So altogether, if we combine, summarize in a single table, so it will be like this. Just we will see as a summary until now whatever we have seen. regarding the properties. So the first one, that is the size, there is increase but discrepancy you can find between these two, and it is very important feature, that is statement, sorry, not statement, I am trying to say it is very important observation that you should keep in mind, because just because of this property so many other things are affected. Okay, so when we will discuss problem, you will be able to understand what I am trying to say now. So from 143 it is decrease, which is unusual, and then we have ionic radius, that is the common oxidation state is M3 plus. So M means any of these element, boron, aluminium, gallium, whatever. So when it is boron 3 plus, it is 27. When it is aluminium 3 plus, it is 53. Now you can see when you are considering the ionic size, there is no such discrepancy. It is only for atomic radius when you are considering the neutral atom. If you are considering B3 plus, then aluminium 3 plus, gallium 3 plus, there is no such discrepancy. Okay. Look at the density as it is mentioned in the left hand side table, 2.35, 2.70. Then there is basically increase, and the reason for this increase, that is also mentioned here. Ionization energy. So as we have seen, there is discrepancy. See, when you are moving from aluminium to gallium, normally it should decrease, but there is marginal increase, almost same, but marginal increase. Then from 578 to 558, it is again decrease. So the discrepancy is for this pair and for this pair, because when you are moving from indium to thallium, 558, then 590. So these two are the discrepancies. Okay. And then the second ionization energy, third ionization energy, that is also mentioned here. Okay. Electronegativity, see, when you're moving from boron to aluminium, there is decrease, and that is expected. But after that, there is slight increase, but that is not expected, right? But observation is so. Melting point. So these two values we have already seen. This is unusually high, and for boiling point there is a smooth decrease as you are moving down. Now one more thing you can see here, which is standard reduction potential. Okay, so standard reduction potential for M3 plus M system, as it is the that is the general format we use for representing it. So it is, you can also write the equation M3 plus, that is boron 3 plus or aluminium 3 plus, accepting 3 electron, and you are getting neutral M, that is neutral boron or aluminium. So for this process, the SRP value, that is standard reduction potential value, you can see. So the first 4, it is having negative value, and the last one, that is positive. So more negative means it is having more reducing capacity. Okay, so reduction potential value, if you are getting any problem which is asking the order, to find the order, then you can check it from this. Fine. So here we have a problem where we have to apply some of these properties. Which of the following statements are correct regarding the general characteristic of 13 group elements? The first statement, the 3 statements in blue color, decreasing order of electronegativity of group 13 elements. Remember, when you are moving from boron to aluminium, there is basically decrease. But after that, from aluminium to gallium, from gallium to indium, from indium to thallium, there is marginal increase, right? So maximum value, just have a look in the previous slide. So maximum value is for boron, right? After boron, it is Tl. Then indium, gallium, aluminium. So aluminium is at last. Btl in gallium Al. That means this is actually correct. It is true. Fine. 1 is true. That means it will be, if you look at the options, either A or D, any of these 2. You have to choose because only in these 2 you have 1. Then look at the SRP values decreases in the order. So maximum value mentioned for TL, and that is true. Remember, it is the only one which is having positive value, and aluminium is maximum negative. So here again see, TL is maximum. After that, the next one is indium. Then obviously you have to consider the negative value. It is not based on only the numerical value. Then we have boron and then alum. TL, indium, gallium, boron, aluminium. So this is also true, isn't it? That means 1 and 2, these two are true. But why the third one is not correct? It is saying that gallium has high melting point because of its polymeric nature. But gallium is not having high melting point. It is actually having lowest melting point. Remember, close to room temperature, we have just discussed at summertime. You can see it even in liquid state, isn't it? So it is not high melting, it is low melting. And also some explanation is there. But we don't have to go up to explanation part because it is not high melting point, it is wrong. So this is false only. The first 2 are correct. So option A is the correct option. Okay. So after all these properties, next we will see oxidation state. Though some initial discussion we have already seen regarding oxidation state, but that is in the last class when we have remember the slide where the general discussion I have done regarding all the groups of P block. That is a general discussion of P block, not for specifically for group 13. So there we have some have seen the oxidation state, how it should be. So now we will discuss it in detail. So in the table you can see the first 2 elements plus 3, which is basically the group oxidation state. I am writing here group oxidation state. This is also group oxidation state. But when you have the next 3 elements, that is apart from the group oxidation state, you also have this extra oxidation state. Now to understand oxidation state, we have to write the valential electronic configuration, which is NH2NP1. So if you are removing the first electron from NP, you will have oxidation state +1. But if you are removing all the 3 electrons, that is you are removing the NS2 electrons from NS and you are also removing the single electron from NP, then you will have +3 oxidation state. So it is clear from this table that for boron and aluminium, 3 electron removal, this process easier. But for the next 3, if you remove, though it may vary, it is not that always you will have these 2 oxidation state, but it may vary depending on with what type of other element it is making the compound. Depending on that, it may vary. But +1 is also observed. That means in these 3 elements, single electron removal from NP, it may happen. So all these elements can show a maximum of +3 oxidation state because more than that is not possible. If you are saying that why not more than that, so more than +3 not possible because in that case you have to break Ng configuration noble gas, which is not possible. So this is the maximum oxidation state you can have for this group. Now because of inert pair effect I have already discussed in last class in general, that is before starting group 13. You can also check it there. I am not going into the details again because same thing will be repeated again. But the reason is inert pair effect. Because of inert pair effect, the heavier elements means especially indium and thallium. So in this case, the heavier elements of group 13, they show oxidation state 2 unit less than the group oxidation state. Basically, this statement, it is not just for group 13, it is also applicable for the next 2 groups, 14 and 15. But here for group 13, group oxidation state is, this is +3. And 2 unit less, that is +1. So +1 is also observed. But specifically for heavier elements, reason is inert pair effect. Now what about the order? Order for +1 oxidation state increases like this. So +1 oxidation state is most probable in case of TL Then it is probable for indium, then gallium, then aluminium. Actually for aluminium it is almost nil. You will hardly see any compound of aluminium in +1. It is mostly +3. Okay. Now for gallium, +3 oxidation state is more stable than +1. So I am writing it here. For gallium, +1 less stable than +3. Okay. Both gallium plus and indium plus salts, they undergo disproportionation reaction in aqueous solution. Sorry, for both these, not just for. So for both of these, +3 oxidation state is more stable. So see, it is still +3 oxidation state is predominating. Though +1 is observed, but +3 is still predominating. But when you will reach TL, now you will have solely +1, which is more stable. So disproportionation, it means the oxidation state which is already there. Look at this formula, GaX. X is suppose any halogen. So here oxidation state is +1 because from the formula you can understand halogen is always -1 oxidation state. So it is +1. And when it is undergoing disproportionation, from +1 it is becoming 0. That means it is gaining electron. This is reduction. It is also becoming Ga3 plus. And counter ions are there. It is actually GaX3, but just to show the oxidation state, it is written in this way. Just combine it, it will be GaX3. But whatever it is, oxidation state is +3. So from +1 now it is +3. So this is reduction. Sorry, this is oxidation. This is reduction. So both reduction and oxidation occurring simultaneously, and that is actually disproportionation, right? So what these equations, from these equations, what conclusion we can draw? We can draw that disproportionation is happening here. It means it is trying to move from +1 to +3. That is why this disproportionation is happening. It will prefer to stay in 3+. So that is why from +1 it is converted to +3. So disproportionation is possible for gallium and indium. And for the last one, thallium. See, thalose compounds. Thalose means when TL is having compounds in +1 oxidation state, then you can call that oxidation state thalose. Just have remember when iron is 3+ and when iron is 2+, what we call them? We call them ferric and ferrous. So just like ferrous, now TL is having the lower oxidation state, which is ending with us, OUS. So thallus, the lower oxidation state. Compounds of TL, that is TL plus, for example, TLOH or TLCl. So HO minus single negative charge, Cl minus single negative charge. So these are thalose compounds example. So these are more stable than their respective thallic compounds. So thallic, just like ferric ferrous, thallic thalose. TL3+. So respective thallic compounds means if you are having TL3+, so the formula for hydroxide will be like this. Formula for chloride will be like this. But TLCl, thallium chloride, is more stable than thallium trichloride. Or this one is, that is TLOH is more stable than TLOH whole 3. So thallic compounds are less stable. So it means what? It means for TL, now +1 is more stable than +3. And for these two, there is no question of +1. Okay. So this is the variation of oxidation state. Now, when you will actually see their chemical properties, that is how they are reacting with halogen, oxygen, then you will see the application of this oxidation state, and you will see different types of compounds. So suppose TL is reacting with some halogen, so mostly you will have compound like TLCl. But if it is aluminium, the formula will be LCl3. So the reason is this, that is oxidation state is different, and how it is changing down the group, all we have discussed in this slide. Fine. The problem is saying the increasing order of atomic radii of group 13 elements. So here we have the 4 elements. Boron is not present. So regarding the discussion regarding size, we have in the last class, not in today's class. So this table I have shown to you, where the atomic radii in picometer you can see. So from 85 to 143 there is increase, but after that there is decrease, and this is the part where discrepancy is observed. So maximum is for TL. This is not correct. TL will always have maximum value, but after TL the next one is indium. That is also fine. So this is also cancelled, but after indium it is not gallium, it is aluminium. So option B should be the correct option. It is very straightforward question, nothing to discuss. The reason obviously we have discussed it several times. I am not going to that. That is why gallium is having lesser size than aluminium. That is already discussed. Okay, the next problem is regarding oxidation state. Relative stability of +1 oxidation state of group 13 elements follows the order. So I will again write all the elements because here, okay, boron we do not have, aluminium, gallium, indium, TL. So the tendency to show +1 oxidation state, it is obviously maximum for TL, and after that it is indium, then it is gallium, and it is almost, that is, it is not observed actually, not at all. So option 4, that is the correct option. TL is maximum and aluminium is minimum, and in between these two are also correct. Okay. Trends in chemical reactivity. So what it means actually, trends in chemical reactivity, it means that whether they will form covalent compounds or they will form ionic compounds, or also regarding, that is, information regarding the oxidation state, all these things we will discuss it. And what type of compounds you can expect, right? Now for the first element, which is boron, the sum of its first 3 ionization enthalpies, that is ionization energy 1, ionization energy 2, ionization energy 3. If you can provide all the required energy, then only you can form free boron 3 plus ion, right? So if you want to get B3 plus in the cation form, that is when we are talking about ionic compounds, then this free cation must exist. Otherwise, ionic compound we cannot see. And when we say that covalent compounds, there is actually no free cation like this, because in covalent compounds there is actually sharing of electrons in the covalent bonds. So when it is very difficult to remove electrons, and this type of B3 plus free ion formation is difficult, then obviously it has to make covalent compound. So that is mentioned here. Because the sum of the first 3 ionization energy is very high, we cannot provide it so easily. So it cannot form this type of free ions, but it has to form covalent compound. It has no other option. And covalent compound means sharing of electrons, that we know happens in covalent bonds. That will take place. For the next element, aluminium, the sum of first three ionization enthalpies of aluminium considerably decreases. Now these values you can get from the table. Remember, 2 slides before we have seen a table where all the 3 ionization enthalpies you can get. You can also check it yourself. So now the summation of first ionization enthalpies for the next element, considerably there is some decrease. And that is the reason aluminium now can form 3 plus ion, unlike boron. And basically aluminium is very electropositive metal, which is also clear from the SRP value, standard reduction potential. Okay. So example of the second statement. Now we will get in this third statement, as it can form Al3 plus. So this AlF3 compound or Al2SO4 whole 3. Sulfate ion means 2 negative charge. 3 means total negative charge minus 6. And 2 aluminium, that means total positive charge plus 6. Fine. So Al2SO4 whole 3, aluminium sulfate or aluminium fluoride, they are ionic in nature because +3 ion formation is possible. But for this type of compounds, AlCl3, AlBr3, Ali3, now the anions are very high and they are highly polarizable anions. Not just high, they are highly polarizable. And when we have very large polarizable anions, polarizable means where the electron density can be dragged easily towards the cation. In those cases, because of polarization, suppose I am drawing the aluminium 3+ here, and here we have a Br minus, which is very large in size. Now there will be some polarization. So see how the negative charge is dragged towards L3+. So when this type of that is, it is not separate charge. Suppose if it is completely separate, then aluminium 3+ is like this, and Br minus, it is like this. But when I am saying that there is some polarization happening, now it will be dragged towards this. So ionic character is gradually decreasing and covalent character is increasing. Basically, it is based on Fezan's rule, which we have discussed in chemical bonding chapter. So there you can also check that chapter, that how when polarization is very high in any ionic compound, then covalent character is generated, and that is actually according to Fezan's rule. So this type of now, as it is not separate Al3+ or separate Br minus, there is some sharing happening as if, so that is why covalent character is introduced. So these three are covalent in nature, but these two ionic compound. AlCl3, GaCl3 and Cl3, they are covalent when anhydrous, but they are ionic in nature in hydrated state. So what happens when it is in aqueous solution? Some hydration is happening. Hydration means different H2O molecules, it will surround the cation. Suppose here the cations in general I am writing M3+. So it will surround this metal, and as a result it will stabilize this free M3+. And this type of stabilization is only possible when you are taking it in water medium. Then only water molecules are surrounding this M3+, making it stabilize, and that is actually hydrated condition or hydrated state. So when they are not anhydrous, when you have taken it in water medium, there will be now it is no longer covalent, it is ionic in nature. Okay. The change from this covalent character to ionic nature, it is because of this reason that in aqueous solution, hydration enthalpy compensate the ionization enthalpy. What is the meaning of this? So one explanation, I hope you have already understood, that in water medium when you have taken it, there is no longer any covalent character, because now you have, okay, I'm taking any metal so that it will be easier for you. So now it is surrounded by water molecules, and that is why it is solvated, it is stable. So when it is solvated by different water molecules, there will be hydration enthalpy that we have to consider. So when any cation is solvated, that is hydrated, because now the solvent is water, so I am using the term hydrated, not the general term solvated. So when it is hydrated, some energy is released because the system is becoming more stable. So when system is becoming more stable, some amount of energy is released. So this released energy, that is hydration enthalpy, which is del H hydration, this is actually negative. So some energy will be released, and this energy which is released, that can compensate the ionization enthalpy. Because when you are making Ga3+, you have to provide ionization energy 1, ionization energy 2 and 3. So this combined energy value, if it is, that is a numerical value, if it is lesser than this, that means some excess negative charge is there. So it is compensating. So as it is compensating, so ionization enthalpy, as if this energy that you have to provide, 3 ionization energy, as if it is coming from the stabilization energy, hydration enthalpy. So this is the reason that there is some change occurring. Covalent nature is gradually converted to ionic nature. Okay. For BCl3, AlCl3, GaCl3, the increasing order of ionic character. Now, ionic character introduced, and if we talk about covalent character that will be high when polarization is high. Basically, when polarization is high, covalent character will also increase. When polarization is very high, when charge density is very high. Charge density high means polarization high, covalent character is high. And charge density means charge by size ratio. Now, if you look at these compounds, here we have total 3 compounds, BCl3, AlCl3, GaCl3. And here charges are same, all are having +3. But size is different. Boron, aluminium, gallium, as you are moving from boron to aluminium, gallium, remember, boron is smallest and aluminium is slightly greater than gallium. So if we consider size, aluminium, gallium, and then, sorry, let me clear one thing. I'm not talking, when I'm saying size for in the ionic state, that is not the atomic size. Now they are not ion. Now this explanation is not applicable. Now down the group there is increase in size. So this is for atomic radii. Okay. Ionic character is inversely proportional to polarization power of cation. So polarization power is inversely related to ionic character, right? Now here polarization power, basically here we will consider the atomic radii. That is, when we are giving the explanation, we have to consider atomic radii, don't consider the ionic radii. It is true that for ionic radii down the group there is smooth increase, but when we are giving the explanation here, we have to consider atomic radii. So size, if you see, it is maximum for aluminium first, after that it is gallium, and then it is boron. So as I have said, that polarization power inversely related to ionic character because it is directly related to covalent character, and polarization power is related to charge by size. As charge is same but size is changing, so that is why just considering this denominator when it is smallest. So it is smallest for boron, right? So smallest means here charge density that will be maximum for boron. So covalent character that will be high. So ionic character will be minimum for boron. So this should be the correct option, because as for aluminium size is maximum. Size maximum means charge by size or charge by volume, whatever you say. Here charge is same for all, but size is maximum. That means here polarization power that will be minimum. This ratio will be minimum. That means polarization power is minimum for aluminium. As it is minimum, that means ionic character that will be maximum for this. Okay. So in this way, we have to choose option C. So trends in chemical reactivity, we will continue the discussion. It is not complete yet. Since the ions in +1 oxidation state, they are much larger than the ions in +3 oxidation state. That we know and that is expected. So the compounds of these 3 elements, GaIn, that is indium and thallium, when they are in +1 oxidation state, then the compounds that you get, and when they are in +3 oxidation state, then the compounds that you get. If you compare their ionic character, obviously +1 state compounds, they will be more ionic, because ionic character, covalent character, it is directly related to size that we have just seen in the previous problem. In trivalent state, most of the compounds such as ECl3, so this E is basically, E may be any group 13 element, okay? So this is just example of trivalent state compounds. So in trivalent state, most of the compounds of group 13, they are actually covalent in nature, and that is why hydrolyzed by water to form either tetrahedral species like this. Suppose I have taken B, so it will be BOH whole 4 minus, and it is sp3 hybridized because surrounding E there will be total 4 coordination, and 4 coordination means it is sp3 hybridized. Fine. But another type of species may also form, which is EH2O whole 6. Now when EH2O whole 6, that means total 6 coordinations, and 6 coordination means now the hybridization will change. It will be sp3d2. So depending on different elements, when you are treating these elements in their +3 oxidation state with water, that is hydrolysis reaction, in some cases we will get tetrahedral species. Type is EOH whole 4 minus, and here the hybridization will be obviously sp3 because of 4 coordination, and when it is octahedral species, then because of 6 coordination, now the hybridization state will change. It will be sp3d2. BCl3, when undergoing hydrolysis, it can form this type of tetrahedral because there is boron is from second period, right? Principal quantum it is 2. So as it is from second period and there is no d orbital. So no d orbital means sp3d2 hybridization not possible. Only 4 coordination is possible. So BOH whole 4 is the species that will form. So it cannot expand its valency beyond 4 because of absence of d orbital. What about AlCl3? When it is AlCl3, now on hydrolysis, it can give octahedral species like this. So see, it is matching with, and this one is matching with EH2O whole 6 3 plus species. Because aluminium can expand its covalency from 4 to 6 because of presence of 3D. Just again have a look. Suppose we have NS orbital, then we have NP orbital, and in some periods, that is period 3 onwards, you can have 3D. Let me write ND. It is actually N is 1 less. When that is compared to N will 1 less. But whatever. If D is present, then what can happen? These orbitals can also take part in reaction. That is coordination number 6. That means 2D orbital must take part in bonding. And that is possible if D is present. But in case of boron, that is not present. So that is why we are getting different types of species. From BCl3, we are getting 4 coordinated. From AlCl3, we are getting 6 coordinated species. Okay. In trivalent state, the number of electrons around central atom in a molecule of these elements will be only 6. Just take BCl3 example. Here we have total 3 boron-chlorine bond. How many electrons are involved? One is coming from boron, another one is coming from chlorine. But surrounding boron, if you count how many electrons are there, it is only 6 electrons. Now 6 electron means octet is not complete. So there is some electron deficient nature which will be generated. So they will have a strong tendency to accept a pair of electrons so that they can fulfill their octet. And this is the reason for their Lewis acidic character. Lewis acid character means which any species you can call it Lewis acid if it is accepting a pair of electrons from some other species. So if this tendency is very high, that means Lewis acid nature is also very high. So in BCl3, you can expect some Lewis acid nature. And now the reaction we are going to see, in that case, we will be finding this Lewis acidic nature. BCl3 easily accepts lone pair of electrons from ammonia, and it forms adduct like this. Any adduct, we represent it in this way: BCl3 dot, then ammonia. So this is the reaction. See, we have BCl3. and ammonia, this lone pair of electron which is present on nitrogen. Basically, NH3 you can call it Lewis base. So the species which accept electron pair we call them Lewis acid, and any species which can donate electron pair it can be called as Lewis base. So here this one is Lewis base and this one is Lewis acid. It is donating electron. Because of this donation, now there is some adduct formation. Nitrogen is positively charged, boron is negatively charged. In some places you can also see the bond is written in this way. So adduct. So there is some arrow as if the donation is happening from nitrogen towards boron. Now one more thing also you are noticing here that some bond distance is mentioned. Here it is 174 and now suddenly it is increasing 184. So what happens when you have this single BCl3 molecule because of this electron deficient nature, but we know in chlorine there is some more lone pairs that is also present. Now to remove this electron deficiency, what happens? This lone pair can be donated towards boron and as a result you will get some double bond character between boron and Cl. Now boron will having some negative charge and this will be some positive charge. But you see, and this can also happen from other two chlorine atoms. So there is some double bond character. And if you take the average picture, it will be like this, as if all over these three chlorine atoms there is some double bond character. So it is not purely single bond. There is some double bond character, so that is why it is 174. But once there is adduct formation, the electron deficient nature, it is already fulfilled by ammonia. So this type of double bond, that is pi donation, it is actually called pi donation from chlorine, or it is also called pi back bonding. Why back bonding? Because already there is some bond between boron and chlorine, but chlorine is further making a bond by donating electrons. So that is it is called pi back bonding. So pi back bonding is happening here, that is before reaction, but it is not happening here. So that is why now the bond is longer, 184. And also see this molecule is planar in nature, because if it is planar then only this type of electron donation, that is resonance, is possible. So this is planar, but this one is not planar. Surrounding boron, if you see 4 coordination, so it is sp3 type of hybridization. Now this Lewis acid character decreases down the group as the size of the element increases. So if you compare BCl3, then AlCl3, then the next one GaCl3. So in this way, if you move down the group, Lewis acidic character decreases because there is increase in the size of the element, basically increase in size of the cation. So the size of, if you consider with charge, Al3 plus, Ga3 plus, now with charge there is smooth increase down the group, so Lewis acidic character decreases. AlCl3, it can also overcome its electron deficiency, but it is not like BCl3. It happens in a different way. So in BCl3 we have seen that electron deficient nature, how it is removed? It is removed by some adduct formation from with some other species like ammonium. But in AlCl3 some dimer formation is possible. So you can see here we have 2 AlCl3 molecule in red color and in green color. So there is some bonding happening. So chlorine is donating electron towards the aluminium atom of the second molecule, and this green chlorine, which is from the second AlCl3, it is donating its lone pair towards the aluminium of the first AlCl3 molecule. So this is basically coordinate bond. It is not proper sharing of electron between chlorine and aluminium. Both the electrons are coming from chlorine. So that is why it is coordinate bond. Fine. So this type of dimer formation when happening, now surrounding aluminium, so because of this electron donation and surrounding aluminium, there is no longer 6 electron, it is more than 6 electron. So that is the electron deficient nature is fulfilled. Among the halides, the order of decreasing Lewis acid character. So here we have boron, we have aluminium, then we have gallium, and then we have indium. Now decreasing Lewis acid character, we have in the previous slide, see the fourth point, it is mentioned Lewis acid character decreases down the group. So if it is decreases down the group, the maximum Lewis acidic character it will be for BCl3. So 1 should come at first position. After that it is 2, then 3, then 4. So this should be the correct option. Okay. And also if you see atomic radius, it is 2, there is some discrepancy, but for ionic radius in class 2 state, there is a smooth increase. Some extra information is also there if you are interested how the ionic radius in class 1 oxidation state changes. These two no values are possible because there is no such boron, aluminium. So these two are not possible for boron, aluminium, but here you can see it is increasing, smooth increase. Okay. So down the group, Lewis acidic character decreases. So we will finish the topic here. So that is trends in chemical reactivity. That part is complete. And regarding that, we have also discussed some problems. So we will end the session here. In the next class, we will also see their chemical behavior. That is how they're actually reacting with other elements or other compounds. So chemical behavior of group 30 elements we can see. Fine. So we'll end the session here. Thank you for listening.